Hi, GrafanaCon 2020. I'm Dave Worth. I'm here to talk about the Venn diagram of observability from lovely virtual background Amsterdam. This is a public domain image of a beautiful canal where we'd all be. But since we're not, let's talk about observability tools. First off, about me, I'm David Worth. I'm currently an engineering manager at Strava. I've also been and still sometimes act as an SRE at Strava. Before Strava, I was at DigitalOcean for a number of years, where I thank them for giving me a lot of the foundations for this talk. A lot of the ideas that I came from starting there and have been able to do at Strava. It's been very exciting. I'm also a total observability wonk and a graph gardener. I spend way too much time clicking around in Grafana, working on my graphs, improving them, making them really pretty, also making them easy to reason about, and fundamentally better. Ooh, do I want a log scale or a linear scale? It's a question I ask myself quite often. So let me set this talk up. Let's talk about what we're doing here. The service is down, definitely been paged. It's probably 3 a.m. and I'm probably somewhat undercaffeinated. There's some early questions. Who owns the service? Like, is it my team? Is it another team? You probably have a service catalog and ownership sheet. We're not gonna have to talk about that today. You probably also want to answer things like, when did it go down? Why did it go down? Where is it running and deployed? Hopefully that's to a standard platform as a service or other deployment mechanism. Maybe not. How to get into that state? And that's actually the same as why. So we're really going to focus on when, and sometimes that's not obvious, and why. That's the subject matter for today. Well, there are going to be teams that do this. It's down. That's bad. Maybe we can turn it off and turn it back on again, which does work sometimes. There'll be much better and more prepared teams who have good hypotheses as to why the service is down, usually because they have some observability tools. That's a great state to be in. And then there's the even better case. The service is down because, concrete answer, we know what it is, and here's how we fix it. And that's often because a team is really focused on their observability tools and their services using them. So there's great news. Your team probably already has at least some of the tools or will shortly, and hopefully if you already have some tools, you have even more than you think based on this talk. First things first, there's 4 primary observability tools I'm going to talk about today, and I'm actually going to dig into some of their properties. That will set up the second half of this talk where we talk about their intersections. One caveat, this is not a vendor talk. Ironically, at GrafanaCon, I probably won't talk about Grafana. I will talk about logging systems, error or exception handling systems, instrumentation systems, and distributed tracing systems, and how they're connected. I will not be pitching any one implementation of any of these, though I will name a few because I've got experience with them. They are common enough that you may also be using them, and they are example implementations of a system. It's not to say they are the best or the ones that I think you should use, and you may have totally different tools, but the concepts we're looking at should apply to those as well. So here is my very careful Google diagram of a Venn diagram of observability. You see there's 4 rings, the 4 that were on the prior slide: logging, error handling, instrumentation, and distributed tracing, and there's some overlap. And you see we've got things like error logs and error rates and timing information, error rates and call traces and outcomes. And there's actually other intersections we'll talk about that aren't easy to stick into this diagram, but this kind of gives us the lay of the land. All right. Let's get into some deep work and talk about the individual pieces that are important here. First, let's talk about logging. You have almost certainly logged. If you write web applications, if you write back-end systems, they probably come with some manner of logging system built in. Python has the logging package. Rails has a logger. Go has numerous logging implementations. Whatever Java apps have tons of logging implementations. You almost certainly have done some logging. What are logs? They're just text, right? They often have various levels that you can filter on. You want to be able to say, well, what's really bad? It's either fatal or an error. What's something we should pay attention to, like a warning or a notice? What's some just kind of information? Sometimes you use that for I got here debugging. And sometimes you want a whole lot of logs to debug a system. There's also kind of 2 major classes of logs. There's unstructured logs, which is a default. We look at old syslogs or kind of traditional logging systems. It has some log levels, some timestamp, and some text body. Depending on the implementation, it can have other information, but it's not necessarily machine readable. So what's structured logging in comparison? Well, it's a format for logs which enables both humans and machines to read them and operate on them. What's super powerful about that is You as a consumer can read them directly and reason about them in the same way you would unstructured logs, maybe with a little bit of parsing. But you can also, if you use a format that is machine readable, write small programs to analyze those logs, especially when the log volume is really large, or there's other context you need to extract, like you need to do some aggregation. There are a few standard structured logging formats. One of them is the CEE format. I've used that quite a bit. There's also kind of other just more generic JSON formats. You can even include logs in protobuf or Thrift or some other wire protocol, as long as that can be consumed by a machine and by a human through, again, maybe a small tool. You've got a perfectly reasonable structured logging system. Here's an example of some unstructured logs from one of our HTTP or Linkerd HTTP balancers at Strava. Nothing particularly important. This came out of a little bit of debugging we did one day. The little command at the top is how we access our platform as a service. And wow, it looked like we were in kind of a bad state with maybe the metrics exporter that day. But as you can see, not a lot of structure to these. There's this level on the left, warning or alert. I don't even know, those aren't even timestamps. Actually, that's a little bit embarrassing. There are timestamps later where you see like May 1, 2019. It's really happened. This is readable by a human, and with a little bit of squinting, you can probably make sense of it. But shoving these logs into some sort of program to parse them would be much more difficult. There's also this raw or structured log, quote, raw structured logs. This is from one of our Rails apps. This is just JSON. Right. What's neat, though, is if you dig through, you can actually get a lot of context about what happened. It's an info level. It was on a login route that was being handled by website controller, which seems like a thing that would help. And it happens to have a message about, this is actually the message field we use, the OAuth view helper. Is this the most helpful log in the universe? Perhaps not. But it does give you a context of what a structured log might look like in your environment. So what do structured logging combined with centralized logging do? Well, centralized logging is a capability. A capability is different than an implementation. It gives a single tool that allows you to do more in a uniform way as an organization. In this case, it's a centralized logging system. It's a single repository from which to examine all the logs of all systems in an organization. It also, by using structured logs, allows you to do aggregation, visualization, other analysis on them, which can be very, very helpful, particularly during an incident or understanding kind of long-term behaviors of a system. What's really, really nice about this is you know exactly where to go to find the logs for any system you're interacting with, not just the one-off path to the logs for a single system, which might be different across every service. You don't want that. Centralizing your logs allows you to look in one place all the time for your logging information. The next part of our Venn diagram is error handling. Error handling has a couple of names. Sometimes it's exception handling. It's usually done by some service. In this case, this is a picture of Airbreak, which we use in Strava. There's also things like Sentry and other both external and on-prem services you can use that you can wire up to your applications to capture exceptions. Just as a reminder, an exception is something bad that happens that you usually can't properly recover from, but maybe you do. With an exception, there's a whole sorts of extra information. There's a stack trace, there's context around the call, and exception and error handling services really lean on that because they include context. Specifically, I said stack traces. That really helps you understand where the code broke in relation to the code that is deployed. It's nice to have a copy of that to look at. Also, some request context. Now, like I said, this is a generally external system that is tailor-made only for one job. It's kind of a scalpel. Its job is to help you take structured information in the form of an exception and the extra context around it and digest it as an engineer debugging a system. Next up, we have instrumentation, which is actually kind of my personal favorite. It's an amazing capability we haven't before. It allows you to measure things in all new and exciting ways. So what are instruments? Instrumentation tools are your empirical friends. They help you measure. Instrumentation systems share a few concrete primitives that we just call instruments. The first one, most common one, counters. They go up and to the right, by definition. Sometimes they reset. That's okay. Counters count things. It's a tautology, I know. They can only increase, and they're great for counting the number of requests at an endpoint, or number of errors, or number of anything else that you are observing in your system. So in particular, they facilitate questions like, how often does that happen? Do you get that request once a day, once a week, once a second, 10,000 times a second? It also lets us talk about rates, which is much more important. How many times a second does that happen? How many times an hour? How many times a day? Or simple things like, what's our error rate? Which is often not so simple. They also enable you as a side effect to determine things like SLOs and make some decisions about, well, today we're seeing this many errors. We should probably guarantee that we do no more than twice that if we're going to expose something like that to a customer. Next up, we have gauges. These are up and down and bounded. They record the current state of something, a resource that has both known upper and lower bounds that can't be violated. Some examples are disk usage, memory usage, network throughput. There's actually a lot of other things that came up when I was thinking about this. Yeah, sure, disk memory and network, but also the number of concurrent requests to a service, number of threads in a thread pool or Go routines, number of messages in a queue, number of processes or auto-scaled instances of a service, number of open file handles. That one bites us on occasion, or connections to a service. They are fundamentally just like the gauge in your car, if your car has round gauges. Though you might think the speed of your car is unlimited, it probably has a maximum. It probably gets worse over time. The other one I often think of is like a pressure gauge on some sort of mechanical system, like a pneumatic system. You have a gauge on there. If you exceed that, you probably can exceed that, but something else probably blows up, and that's real bad. So there's a kind of fundamental bound to it. Computers are a little bit more concrete. Usually we have like a concrete amount of disk or a concrete amount of memory, but this gives us a way to understand where we are with relation to some boundaries. Then there's timing thingies. And I am intentionally being vague here, even though I have some very specific ones I like to think about. They're an instrumentation system to allow us to kind of time things in general. Often there's something called a histogram. We'll talk about that in a second. And they help us to answer questions about things like, what's our 50th percentile? What's our average? The 50th percentile being median and average being mean. Those are different things, but they can help one another, or they're related to one another often. You can also have the 90th percentile, which is like, what's the worst 1 in 10 experience for an endpoint, for example. This cool grayed out thing in the bottom is a particular histogram from one of our systems, a health check. So what are these Prometheus or these timing thingies good for? Well, in both Prometheus and StatsD, they have histograms. Histograms are collections of buckets of varying values that allow you to say, for any given request, which bucket does it land in? So you can think about, say, the timing of an endpoint for a web service. It probably happens. It's possible that a request will be satisfied in less than 1 millisecond, less than 10 milliseconds, less than 100 milliseconds, less than 1,000 milliseconds. And as usually you say, anything that took longer than some upper bound, that's the infinity bucket. That's like real bad. We should definitely count it because it occurred, and we should know that we're doing real bad once in a while. Badly, excuse me. But they give you the ability to first put things in buckets, and then based on those buckets, you can use some interpolation and get out values for, say, the percentile values we talked about a moment ago. Because very often you use these to analyze network latency or client latency. It's also very helpful to observe both internally your service. You think that you, on average, or say P90, respond within 30 milliseconds. And if you also instrument your clients, they may say, no, but it takes 200 milliseconds to get a response from you. That difference could be chalked up to any number of other systems. You should probably think about the fact that your client's experience matters more than your own experience, your own observations about your system. For example, you might have extra network latency. It might be something completely outside your control, like literally networking hardware or slow cellular systems or something else. It could also be internal routing systems like a service mesh. And by being able to compare client and server experiences, you can identify gaps and then investigate what's causing those gaps if they're unacceptable. Finally, the most complicated of the four, distributed tracing. This is probably the last tool that teams add to their stack. Most teams will have logging, error handling, and instrumentation well before they even consider distributed tracing, but that does not mean it's not very, very valuable. So before we talk about distributed tracing, what is tracing? So I'm going to talk about the non-distributed tracing case. Tracing within a single service is a collection of what we call spans. They're essentially just start and end timestamps for some events. And then maybe some extra information about what is being measured by those start and end timestamps. usually wrapped around some body of code. That could be a database query, that could be an HTTP request, that could be a non-HTTP request, some other RPC, that could be perhaps querying against a cache, any number of things that you might care about the performance of within your system, and also the error state of within your system, can be captured by spans. Moreover, you treat them as a tree. So you'll have some sort of parent span with multiple child spans. Example of that might be something like this, where you have some sort of start time and end time for a request to your service. You might start by trying a cache and missing it. The parent-child relationship is represented by parents are above children in this case. So in this case, this overall request span has 4 children spans. This cache miss thing. Next, since you missed the cache, you might have to actually hit some database. You might have a query wrapper, something that actually is not a direct interface to your database that allows database access, but might also allow a service access. And you want some uniform interface to that. Well, that probably also has some overhead. So you'll note that the database query itself seems to run in a slightly shorter time than the query wrapper itself, because there's a little bit of stand up and tear down time for that wrapper. After that, you've hit some database. You probably have some external service you have to care about. You can call it. That takes some amount of time. It's a lot of time because you probably have some network latency as well as the service latency itself. And then you might render some HTML at the very end of this whole cycle. As you can see, you have the parent-child relationship of a bunch of time measures. This is the fundamental principle. So tracing becomes distributed tracing when there's a unique identifier for every trace, and that's propagated across the systems for every system servicing request. So for example, we had the service call before. If in that service call we pass down request ID 1234 and it uses it, we suddenly can distribute this trace and aggregate them. By aggregate, I mean make them all part of a single overarching trace across a whole bunch of systems. Here's an example of that. Exactly. So earlier we had the service call with the ID. Now we propagate it. That service itself also has some database query. Maybe it has a wrapper, maybe it doesn't. It also does some hard calculations. It has to go off and look at a whole bunch of historical data and generate some aggregates. There's maybe some calculation pipeline. There's a bunch of those all happening. They also carry that trace ID. And then when that's all done, comes back up and we render the same HTML we did before. So now in blue, we have one set of traces, and in green, we have another set of traces from a different service that are all tied together by that initial request ID. So now what? This whole thing was called Venn diagrams. Venn diagrams are all about talking about intersections. We've talked about the tools. We've talked about what we're going to call primitives of observability and observing your software systems. But if this is a Venn diagram, how do they fit together? Where do they overlap? So instead of emphasizing the systems now, let's talk about some of the intersections. Like I said earlier, error logs, error rates, timing information, and call traces and outcomes. There's always some overlap in this Venn diagram. We're going to use the little caret symbol to mean intersection. Let's talk about where error handling and logging fit together. Well, the error handling or the error handling service and the logs often answer kind of the why of an incident, like we started with. You may not have an external handling system, or it might just be down, right? You might have a great service you love, but they're also having an incident. So they're not capturing exception logging. What can you do in that case? Well, if you also log your exceptions, especially in a structured logging system, to some sort of, centralized logging system, you suddenly have another copy of that same information. It may not be as good. It may not present it in as informative a way. It may not be a perfect one-to-one match, but you can almost certainly ensure that you log sufficient information for any given exceptions or errors in such a way that you can query it later and get at least some extra information. This also means you may not need an external logging system. At Strava, we actually do both. We have an external error handling service that a lot of people really like. We also log all of our errors from our main application. And in general, we try to do the same for all of our microservices. And we log them, in some cases, we log them through our own collection of errors separate from our main application logs. In other cases, they're kind of interleaved, but we do have a way to drill down and find errors. This is sometimes helpful to detect the root cause of a bad deploy, for example, or some sort of external service dependency causing issues in our services. You might capture that externally, but you can also capture it internally with your existing logging infrastructure. So here's a couple of exceptions. We actually have, like I said, we have an index in our Elasticsearch cluster where we preserve all of our logs. If you look at the top, we have a little bit of some container information, the environment that we're in production, and then we have a backtrace. We actually have the stack trace that we have in our exception handler. It is unreadable in this case. We'll talk about that in just a moment. At the bottom, we actually capture the exception class and the exception message. We also have a session identifier, which probably is helpful. This gives us some context. This is hard to read, I admit. I would not, as a responder, like this. In fact, even though I prefer the logging method rather than our external service, this is not how I view the logs when I'm looking at some of our exceptions from the Rails app. Total implementation detail might be a superpower in your environment, maybe. If you happen to use Elasticsearch and Grafana and you happen to log your exceptions in JSON, and those JSON objects have a field that contains your backtrace, which happens to be new lines separated in the way ours is, check it out. Or not new, excuse me, not new line separated, rather comma separated list of strings like we have. Those render as this long, kind of difficult to read line that's unreadable here. And if you look at the JSON view, there's the backtrace down below. Suddenly you can see the exact same thing. Is this a perfect experience? No. Is it as ergonomic as an external exception system? No. Does it work very, very well? Yes, it does. And depending, you might have a kind of heterogeneous environment. You might have some services written in Go, and some services written in Scala, and some services written in Python, and some services written in Ruby, and some systems written in Ruby on Rails, and maybe some Java stuff, and maybe, who knows, maybe some COBOL. So the logs themselves may land in your centralized logging system in a somewhat different format, and those different formats may have idiosyncrasies. So in this case, we actually have some Scala stuff. You can actually see there's a request ID on this trace, which I just noticed, which is kind of cool. Even though this is an error, we actually are carrying a apparently signed request ID, which is probably from our centralized logging. But here's a much more nicely formatted stack trace from our Scala services. Oops, there we go. So what about instrumentation and error handling? Well, instrumentation is good at a few things. It's good at counting things. It's good at keeping track of resource utilization. It's good at keeping track of time. When it comes to error handling, the number one thing you care about when it comes to counting stuff tends to be error rates. Instrumentation is great at error rates. Some error handling systems are also good at keeping track of rates. In particular, one of the ones that we use has a little spark line on the left, and that spark line lets us kind of know the relative rate of every exception that's coming into the system and helps us determine which ones we should triage first. So if you don't have an error handling system, your instrumentation might let you at least understand certain error rates if you break them out carefully enough. And vice versa, if you don't have instrumentation, your external error handling system might give you a little bit of extra instrumentation information about, say, error rates of a given type. Logging and instrumentation. And this one is actually for me, initial inspiration for this subject. So it turns out if you're already logging things, particularly maybe you log entry and exit points from functions in your software, you might, and sometimes it might kind of feel like doing, here debugging. When I say here debugging, I mean print, I got here, I got here, I got here. But if you can't just print because it's running on some remote system, use logs instead. And sometimes it's actually really helpful to have that. In particular, it's sometimes useful, maybe at the debug level of your logs, to say, I got here with these parameters, and I'm leaving here returning with these values. And maybe in between, if you have any extra error logging or warning logging, things that aren't going right, or like important things that went really well, but you should really pay attention to, you might have those kind of bookended by the entry and exit points. Turns out if you actually do that, you can also include things like timing information. You can capture the time When you enter the function, you can capture when you're about to leave the function. You can do some subtraction, figure out how long you're in that function, and include that. The reason this was actually the inspiration for this talk is I, at one point, operated a system that I inherited that had logging, but only logging to disk. It didn't have centralized logging. We were at this bizarre point in that company between two instrumentation systems. Our old instrumentation system had become completely unsupported and was just falling over, and actually just at one point fell over, and we just turned it off. We were also in the middle of adopting the next generation system. By saying that some services were already on it and it was working great for them, but kind of the migration of every service, especially across multiple different platforms, just hadn't happened yet. So I had logs. It was actually in comparing the lift to getting onto the modern instrumentation system or getting better logging in place. It was a much easier lift to get onto centralized logging and add more information to logging. So we spent the energy to do that. And by doing so, I was able to suddenly capture some timing information and also some additional information that essentially got me a less awesome, but still very helpful instrumentation system. One other detail about that was that that system happened to be very difficult to deploy for reasons. We improved that as well, but also had great consequences if a deploy went badly. So team regrettably developed some risk averseness. Let me rephrase that. I developed some risk averseness. The rest of the team pushed me out of that, and we actually got past the story and got real instrumentation later, and things got much better. But in that time, we worked to get structured logging, and we actually got instrumentation that we were able to expose in pretty meaningful ways later in a Grafana dashboard that we built. And that really scratched a huge itch. We suddenly understood the system so much better that allowed us to be less risk averse because we knew when things were going wrong and we could deploy more often and move the story along. So if you have logging, you can also have some version of instrumentation. So about instrumentation and distributed tracing. This is really interesting. Distributed tracing is really good at answering kind of the what of an incident. What service is slow? What thing is raising errors? Instrumentation is pretty good at counting successes and errors, but distributed tracing kind of inherently combines those things, right? Well, instrumentation tends to focus on specific services and specific dependencies. Turns out you can tie those two things together. No. Yes, all of that is true. That was not the point I was trying to make. Instrumentation does tend to focus on those things, and you can kind of tie them together. Instrumentation can, if you instrument your client connections, if you instrument your internal systems, you can start to build at least a localized view of a distributed trace. It's not perfect, but it can at least indicate where services are going, where dependencies are going wrong, where internal systems are going wrong. And that's one of the things you get out of distributed tracing. On the other hand, where does logging and distributed tracing fit together? This is actually something of an implementation detail, but it's kind of fascinating. Tracing information can be represented in logs already. If you happen to have centralized logging today, one design decision you can make is that all services log to the same index, which is like a log file within a centralized logging system. You could also decide that every single service should have its own log file. The latter actually, in many ways, is a much simpler and a saner decision. But I've worked on a system where, by default, not always true, but by default, every service logged the same index, essentially a log file. So if every service happened to be logged in the same place, and every service logged the request ID in the same way, then suddenly, just by typing in the request ID into the search language, you're able to get an ordered collection of all of the logs from all the services that are doing anything with that request ID. That in and of itself is essentially that tree structure we described earlier with parent and child spans. If you happen to add some timing information as well, you kind of automatically, with that design decision in your logging system, get distributed tracing for free. Now, even with or without shared logging infrastructure for all of your services, and by shared logging infrastructure, I mean a single index or log file for all of your systems, you can still kind of get tracing information in logs. This is a real conversation between two of our engineers, who are our staff engineers, working on distributed trace at Strava when we were still implementing it. We did a bake-off between a number of distributed tracing vendors. And in the meantime, we decided to write our own trace collector that all services were reported to. And then that collector could export to all of the actual visualization layer vendors we were considering. In the meantime, we wanted to collect the logs. We wanted to ensure that that system, our collector, which is doing sampling and all this other clever stuff, was working. Turns out we could just store those traces in a sampled form in Elasticsearch. Now, that view is complicated. It's not at all the way I would prefer to view distributed trace information. Distributed trace vendors tend to have service diagrams that are in the form of a directed graph where you can click on one and zoom in and do all sorts of analysis and slicing and dicing of the data, and then look at relative spans and like look at aggregate spans and record and combine, do all the things you actually really want out of a fully fledged distributed tracing service. But in the meantime, if you're working on that, you can record spans directly into a logging system, to a centralized logging system, and look at the spans directly, and with a request ID, see all of them and make some decision. You'll note at the bottom of this, there's a section where we describe that tree relationship. This is a child of, there's a trace ID, and here's a span ID. So the trace is the entire collection, and the span is the specific parent. Yeah, so we actually have a lot of information. And we were instrumenting a SQL query. So with just centralized logging, you can get partway to distributed tracing. Do you probably want a different interface on top of it? Probably. Do you probably want to write your own? Probably not, but you might. I don't know. I don't know your life. Either way, this is a good medium step. All right. That was an abrupt transition to the end. That is a lot of information about the way I view instrumentation systems, their relationships, and how you can get a lot of value out of a subset of them by being careful about your data structures, your implementations, and how you fit them together. And you can probably get away with not having all four of them by having a subset of them where you get some functionality of, say, the fourth or the next two, whatever else you need and don't have yet today. Thank you for all your time. I really appreciate your attention. And I look forward to the questions at GrafanaCon 2020. Thank you.